All right. So let's see. So maybe to start with just a tiny amount of administrivia. Hopefully everyone, like regularly and religiously checks the Slack. But if not, I announced a deadline. So on next Friday, a week from today, I'd like everyone to turn in a project proposal. And just to remind you, what is a project proposal? I need you to tell me who, if anyone, you are working with. It's fine to do a project on your own, but you are encouraged and welcome to work with as many people as you like. And I only need one proposal per team. And a rough idea, which maybe comes out to be like a page of what exactly your project is about, which should be, it should state some problem or class of problems that you think is interesting. Maybe tell me a little bit about why it's interesting, and then state generally some approach. Of course, you're not going to know all of the solution yet, but some approach that you are planning to take to think about it and ideally solve it. And maybe some pointers to papers in literature that you sort of hope to draw from, or at least what is the literature if one, if this thing hasn't spawned entirely out of your head, like what is the literature that the dream result that you are proposing to produce would ideally revolutionize. So next week you can just send it to me by email, basically a page-long proposal, what your project's going to be about, who you're going to do it with. Okay, sound good?
Oh, sorry. Can we do it with someone who's from outside this classroom too?
Sure. Yeah. So in general, like the answers to most questions, for anyone listening online, the question was, can it involve partnering with people outside of the class? The answer is yes. The answer to most questions like that are going to be yes. The goal is not to make you, dot all of the I's and cross all of the T's. The goal is to set you on the path to do interesting research, hopefully. So to the extent that that involves collaborating with people not in this class, like go for it. There is not a limit to the team size. I mean, there's probably practical physical limits, but I'm not imposing one. Yeah. Good. Other questions? Okay.
Do you want to tell the students about the deadline of handing in the project that we talked about before the class?
Yeah. So I guess it was asked before the class whether you could turn this in somewhat after the deadline I had announced, but before the date when grades are due. And I pointed out that I had not yet announced a deadline for when they were due. And so I said, sure. But basically, like, like at some point I need to hand in grades. I need, the project to be in before then. And, like maybe let's say the default deadline is probably this class has some scheduled time that the registrar thinks that I would give a final if I were giving a final. The default deadline would be the day of the final, but if you have good reason to need a couple of extra days, that's fine. Again, the idea is to turn in good work and you have to turn it in before I have to give you a grade. Yeah.
So so far the course the theoretical side of
that would be great. Yeah. That's right. So there's, so the way the lectures are organized is we're sort of doing theory, and then we're going to do applications, although I'll warn you up front that the applications are also going to be kind of theoretical. But I do have, if you look at the course website, there's a very long list of related papers, some of which are more practical. The project is very open-ended. So, hopefully you take some inspiration from some of the words that have been said in this room, but do something interesting. And it doesn't have to be, it doesn't have to be a theory project, for example. You also have, so maybe I don't understand the question. What I heard you say was you don't have to follow the proposal strictly for the project. I would like that you propose something related to what you're going to do, but I'm not constraining what you propose. Tell me what you're going to do, and I'll probably be happy with it. Good. Other questions? Okay. Cool. So where are we? So, okay, way back when we studied marginal guarantees, and then we thought to ourselves, these marginal guarantees kind of suck. How can we make them stronger? And so far, we've seen two ways to make them stronger. We could ask that they be calibrated. This means that they should be correct, not just marginally, but conditionally on the prediction that we make. And we've asked that, okay, so that was one way of strengthening them. Separately, we asked, could they be correct in a group conditional way? So maybe I specify a whole bunch of subsets of the feature space, which we called groups. The interesting thing here is, of course, they can intersect. And we asked that we be able to estimate things like means and quantiles correctly, conditional on groups. And so why not both? So what we're going to do today is we're going to think about what's called multi-calibration for means and quantiles. I'll walk you through the derivation for means and refer you to the notes probably for the derivation for quantiles, which is quite similar. And it's sort of a natural combination of what we've done before, just literally asking for both of these properties at the same time. Okay, so the idea will be to specify an arbitrary collection of groups, okay, subsets of the feature space, and then ask that our predictions not only be correct on average, conditional on membership in those groups, but that they should be calibrated, conditional on membership in those groups. Okay, so they should be, and of course, since one of the groups can be everything, this is only stronger than asking for those conditions on their own. So a multi-calibrated predictor, something that satisfies both of these things, will in particular be calibrated. It will in particular offer group conditional guarantees, but it will be stronger than that. It will offer essentially marginal mean consistency, conditional not just on groups, but also simultaneously conditioning on the prediction of the model. Okay. So let's define what we mean. So let's fix a model F from the feature space to the unit interval, say, in a group which, remember, in this class, we generally identify with the indicator function for the group. Tells a function that tells us, are you in the group 1 or are you not in the group 0? The average squared calibration error of F of the model on the group is the following. This is, and sort of what you expect. It's just the L2 calibration error on the conditional distribution, D, conditional on membership in the group. Okay, so remember, and you could, of course, define an L1 or L infinity variant of this, but the L2 variant is going to be convenient for us. And remembering, back to the early lectures, all of these notions of calibration are quantitatively related to one another. So what is this? It's just the sum over all of the values in the range of the function of the probability that the function takes that value conditional on membership in the group. Okay, so this is the probability over a sample from the distribution times the difference between the prediction the model made, which is supposed to be correct, and the actual conditional expectation of the label. Conditional now not just on the value of the prediction, but also on chip in the group. And it's this difference squared. Okay, so it's just, this is just the L2 calibration error, which is the expectation over the value predicted by the model of the difference between the value predicted by the model and the truth, the actual average value of the labels. But now, instead of measuring this over the marginal distribution, we're measuring this over the conditional distribution, conditional on membership in the group G. Okay, so this is just the definition of L2 calibration error on the conditional distribution, conditional on membership in G. We've restricted the distribution to G of X is 1. Okay, and then we'll say that F is alpha approximately multi-calibrated with respect to a collection of groups G if simultaneously for every group in the collection, when I look at the L2 calibration error conditional on membership in that group, this is less than alpha over probability mass of the group. Okay, so we're again allowing, just as we did for group conditional guarantees, we're allowing weaker bounds on the group conditional calibration, the smaller the group gets. Okay, but remember, just as we discussed last time, this is sort of like the right scaling because we're taking sort of a squared error measure of calibration, right? This means that what we're asking for is that the error that we have on some group goes down with the square root of the size of the group, which is sort of the sampling error we would expect. Like even if we just wanted to measure the calibration error on some data set from samples, we would sort of have to settle for scaling like this. Right. Okay. So this is what we want. We'd like multi-calibration, which is just L2 calibration simultaneously on all of the conditional distributions, conditional on membership in these groups. And the way we're going to get it is not so different than the way we've sort of seen to obtain just regular calibration or group conditional consistency. So if you remember, there were these iterative algorithms that we've seen that so far we never really needed, right? So for regular calibration, the first thing I showed you was an iterative algorithm that took a model and then looked for a value V such that conditional on that value, the prediction of the model was wrong on average. And then we applied sort of like a shift. So wherever we predicted V before, predict something else. Now we didn't really need that, it turned out. Like for regular old calibration, we could simultaneously update all of the buckets. And then for group conditional mean consistency and group conditional quantile consistency, we again saw this kind of shift algorithm, right? Like take a model, check if there's any group such that on the conditional label distribution on that group, you're getting the means wrong on average or the quantiles wrong on average, and just shift the model on that group. And then again, we saw, okay, we didn't really need that because for group conditional guarantees, there was again sort of a one-shot algorithm that just solved a single, linear regression problem in the case of group conditional mean consistency, and a convex optimization problem in the case of group conditional quantile consistency that sort of did the same thing. Okay. So here I'm going to show you a shift algorithm for obtaining multi-calibration. And here I think we actually need it, or at least I don't know of a one-shot algorithm that does the same thing. If you could think of one, that would be very interesting. But so far, introducing these shift algorithms has been sort of just a expositional exercise. Like, it turns out that's you don't really need it. But here, we need the shift algorithm as far as I know. Okay. So what are the shifts that we're talking about? So remember, the shifts we've been talking about before, like for group conditional mean consistency, are things like, look, take the old model. We've just identified that the old model predicts on average the wrong thing, conditional in membership in the group. Maybe it was wrong by some delta. And so what we're going to do is output a new model that for members of the group just adds delta to the old prediction, and for examples that are not members of the group does nothing. Okay. Similarly, for calibration, what did the shift do? It said, well, you were wrong, conditional on some prediction V. So we're just going to shift examples for whom the old model made prediction V and do nothing on examples for which the old model made some other prediction. Well, now our, the guarantees, the things we're supposed to predict right on average, are conditional on the value of the model and also on the group. Okay, and so our shifts are going to have to make correspondingly fine-grained updates. So we'll call these group value patches. So given a model F, a group G and a pair of values, let's say V and V prime, both numbers between 0 and 1. The group value patch applied to F at the triple G, V, and V prime is the following function. It's a function of X parameterized by this model F, this shift that I will write suggestively as V arrow V prime and the group. And it's kind of what you might expect from the notation. It outputs V prime if the old prediction was V and we were a member of the group G, and it outputs the old prediction otherwise. Okay, so a very simple update. It just says if, for anyone who was previously a member, or for anyone who is a member of this group G, that doesn't change. If the model previously output V for you, we'll output V prime now. We're shifting the prediction for you from V to V prime. And we're not modifying the model elsewhere at all. It's doing the same thing elsewhere. Okay, so simple update. By the way, for any of these algorithms for which you chain together updates like this, it's sort of very easy to think about how to evaluate the final function, right? Like you sort of start at the beginning, the model you started with, and then you walk forward in the chain and just apply this sort of simple decision rule, which is like an if statement, get a value out, and then you just march forward in the chain, evaluating a single if statement each time, and then you're done. Okay, so if you're worried that we're building terribly complicated models by doing this, we're not, right? Like we're building chains of like if statements, and the convergence bounds we prove in particular are upper bounds on the length of the chain. Okay. So let me give you maybe the algorithm that you'd think of first, which almost works. It's sort of the direct analog of the algorithms we've seen before, but there's going to be one little hitch that didn't come up before that does come up now, and I'll mention what that is, and we'll think about how to fix the algorithm. Okay, so let's call this multi-calibrate. V1, because there's going to be a V2. And it takes as input a function that we're starting with, a target error parameter, a collection of groups, and a distribution. Okay. And it'll have the same template as these iterative algorithms that we've seen before. Basically, we're going to check if our model is already multi-calibrated. If so, we're going to celebrate. Otherwise, we're going to find like the place where it is most, uncalibrated in a group conditional way, and we'll fix it with this kind of patch. And then we're just going to need to argue that this process can't go on for too long. Okay. So so some bookkeeping. Again, it's going to be an iterative algorithm. We're going to keep track of a model indexed by time. So initially, model 0 is just the model we started with, and time is 0. And while our current model, not alpha approximately multi-calibrated, with respect to this class of groups G, we're going to look for sort of the place in which it maximally violates the multi-calibration condition, which is going to be given to us by a pair of a value and a group, right? Like multi-calibration is sort of like asking that for every value our model might output, and for every group, the conditional label expectation is equal to the prediction conditional on that value in the group. So what we're going to look for is the value group pair for which the conditional label expectation is most different from the prediction. So let's just say we'll, this pair VT and GT is the pair that maximizes overall values in the range of our function and groups in G, the product of, what I'm going to write as mu of V and G. So remember, mu of G is the probability of being in the group G. Okay, mu of V and G, maybe I'll write this mu T of V and G because it's defined with respect to model FT, is the probability that you are in group G and you get prediction V. Okay, so it's like the probability of landing in one of these buckets for which we care about getting the conditional expectation right. Okay, so we want to maximize the product of the probability that someone is in group G and gets classified with prediction V times sort of the calibration error conditional on that happening, times the difference between the prediction and the expected value of the label, given that they get given value V and that they are in group G. And in fact, we want to maximize the product of the probability of falling into that bucket times the squared error conditional on being in that bucket. Okay, so like we didn't satisfy multi-calibration. That means on average, basically, these quantities were large. We found some particular buckets on which they were large, and we want to fix that, right? So we were predicting V, but the truth conditional on landing into this bucket was something else. It was like not V. So let's compute what it should have been. Okay, we'll say V prime of t is what the truth should have been. It's just the expected value of the label conditional model predicting V, and the example falling into group GT. Okay, like if only we had predicted V prime instead of V, like the squared error here would have been 0. And so let's patch the model so that that's what's happening. Okay, so we'll just let tomorrow's model, ft plus 1, be the model that results. We're applying this patch operation starting at today's model, applying the patch from VT, what we were previously predicting, to VT prime for everyone in group GT. Okay, so just sort of myopically, right, we found like the biggest like witness of a problem. We just kind of like myopically put some duct tape over it. We like, you know, shifted things so that it wasn't a problem there anymore. And that's it. And then we iterate again. And if, oh, and you know, let's update t. So t equals t plus 1. And then if we ever break out of here, then we'll just return whatever model we get. Okay. Yeah.
I'm sorry, I'm a little confused how we do it in practice. In practice, f of x is a function from x to something between 0 and 1, right?
Sure.
So when we say f of x equals v, in fact, we mean in practice that f of x, it needs to be some kind of being, right? Otherwise, well, that's any number of v.
You're getting at what is eventually going to be the problem. But remember the way we handled this for regular calibration. We sort of said, okay, right, like in principle, even before we sort of introduced the like multi-group aspect, what you're describing is a problem. You know, if f is like real valued, then it might be that the probability of falling into any one of these buckets is 0, because like, you know, you never get the same decimal precision. So we're going to have to work with predictors that have some discrete range. Okay, and it sort of, we'll do this in fact explicitly you know, when we move to V2, but like, it's, yeah, for now, it's not hard to imagine that if you have like a continuous valued predictor, but I round the values to some multiple of alpha, then, you know, I'm not going to like make your calibration error worse than sort of alpha, the amount that I'm rounding to. So we are going to have to ultimately, yeah, to deal with exactly this kind of problem, think about predictors that have a discrete range. Yeah.
So just trying to understand that what's going on differently here from last time. So here the groups don't have to be disjoint.
Even last time they didn't have to be disjoint.
Okay, so what's the distinction between what's happening here in this problem and last?
Yeah, so last week we talked about just group conditional mean consistency, which just meant that, you know, like for all people in whatever group that we care about, like people registered for CIS 7000 or people who thought they were registered for CIS 7000, or, you know, PhD students at Penn or residents of Philadelphia or whatever, the model predicted the correct thing on average, right? For them, if I average over the predictions of the model, I get the average of the labels over that group. Here we're asking that conditional on membership in the group, not just do we get the right thing on average, we're calibrated. So we're conditioning on an extra thing, basically.
So that's what we need this patch have like these two parameters. We need to be the group and then the value that we're calibrating.
Exactly.
Okay.
And so like concretely, the difference between this patch and the patch from last class is that the patch from last class operated only on groups. Whereas the patch from this class is sort of making more finer grained adjustments. It's operating, you know, on a group and a value. Mhm. Good. Okay, so like in general, and you know, like maybe you're not worried about this since you've seen several algorithms of this sort already, but if this was the first time you were seeing an algorithm of this sort, the kind of thing you'd worry about is the following. I mean, like, obviously, if we ever return anything, it's going to be approximately multi-calibrated. That's the halting condition. If it wasn't approximately multi-calibrated, we wouldn't return anything. But the thing you would worry about is that, you know, we're making these like myopic little fixes. I'm going to sort of fix a problem with multi-calibration here, but because the groups intersect, I might be making it worse somewhere else, right? Like I you know, change the prediction to be correct conditional on membership in group G, but like that changes things in a way that's detrimental to correctness for group G prime. And you might worry that I'm chasing my tail, that sort of these patches cause me to go in circles. And so we need to argue again that that's not happening. And of course, like at a local level, that could be happening, right? Like it's not that each of these updates makes things monotonically better for each of the groups. Like that's just not true. But there's going to be a global metric on which we make progress, and that again is going to be squared error. Okay, so let me sort of prove the same kind of progress lemma that we used last time, but you know the way it differs here is going to highlight a problem that didn't arise last time when we were just talking about group conditional guarantees, and is going to require us to like make a little bit of a modification to this algorithm. Okay, so this is the progress lemma. So it's going to say, okay, let's like zoom in on any round of this algorithm, round T. So we're looking at the update that's applied at round T. And what I'm curious about is how much the overall squared error has decreased between round T and round T plus 1. So I'm interested in the difference between the squared error, the Breyer score, at model T and the Breyer score at model T plus 1. Okay. You know, it should go down. So we want this to be like a positive number bounded away from 0 so that we're making quantifiable progress. So the claim is that this is exactly equal to the probability that we predict that model FT predicts label VT, and you know, the example falls into group GT. Right, this is the same notation we used here. Times VT minus VT prime squared. Okay, so here GT and VT are the value and group chosen by the algorithm at round T. Okay, so the claim is that, you know, like the reason we choose VT and GT like this to maximize this quantity is because this quantity is exactly capturing the progress that we make in Breyer score. Okay. And the proof is sort of straightforward. It's like we've seen several times before. Let's just sketch it. Okay, so you know, what is this thing? The change in Breyer score. The nice thing about squared error and also pinball loss is that it's separable over examples. So if I want to know like how much has the squared error changed between model FT and model FT plus 1, I can take any event that partitions the space, like any event such that for every example, the event is like true or false. And I can ask, what is the squared error conditional on the event being true times the probability the event is true, plus the squared error conditional on the event being false, times the probability that the event is false. Now, the event that we're interested in is going to be exactly the event that our model FT predicts VT, and our model, and the example is a member of group GT. Now, suppose that event is false. We've got an example either such that the example X is not in group G, or the example is in group G, but our model predicts something other than VT. Well, then our patch, this thing we did to move from model FT to model FT plus 1, didn't change the model at all. Okay, so conditional on that event not happening, conditional on not falling into the bucket that defines our patch, the change in squared error is 0 because our models are identical, conditional on that event not happening. So all of the action here and the change in squared error is about sort of what's happening conditional on falling into that event, that bucket. Okay, so this change in squared error is the probability that we fall into that bucket. That's just, our notation is mu t of VT GT times the change in Breyer score conditional on this event. Okay, which is just, well, the difference between the squared error of the model before the update and the squared error of the model after the update, conditional on the model having predicted VT before the update and the example being a member of group G. Okay, so what's the squared error of the model before the update? Well, all of this is conditional on the model predicting VT. So the squared error of the model before the update is just the expected value of the prediction of the model, but we know what that is. That's VT. Okay, so that's just VT minus Y squared minus the squared error of the prediction of the model after the update. But again, we know what that is. That's V prime T, right? Because what we did, the update was exactly, if you were in this bucket and you previously were predicting VT, like now predict V prime T. So it's just the difference between VT minus Y squared and VT prime minus Y squared conditional and being a member of group G and the model predicting value V. And remember, VT prime is the truth. VT prime is the correct conditional label expectation. And so we know from sort of the characterization of squared error we proved in the very first lecture what this is, right? This is exactly, well, the probability of falling into this bucket in which the prediction was VT and the group was GT times VT minus VT prime squared. Okay, so we're making progress. Now, okay, so what's wrong though? So this is very similar to the progress lemma we proved last class when we were talking about group conditional guarantees, except last time the event we had to update on, and therefore the event we had to condition on in proving this progress lemma, was just that the example was a member of group G, not that the model predicted some particular thing V. So our progress lemma last time looked exactly like this, except we were looking at the probability of falling into group G. Okay, not the probability of falling into group G and predicting some value VT. And that was great because like what, group conditional mean consistency was a requirement that looked something like this. It was in particular that the product of the probability of falling into group G and the group conditional mean consistency error was less than alpha. And so if we weren't yet group conditionally mean consistent, we knew that this quantity exactly was more than alpha. And so if we weren't there yet, we would make at least alpha progress. Okay. Yeah.
So have we already established that we're going in the right direction, and our only concern is we don't know how fast we're going?
That's right.
Okay.
Yeah. So like,
This should be non-zero.
that's right. It's got to be non-zero because, like, we're not calibrated. Sorry, we're not multi-calibrated. So we know that, yeah, multi-calibration is just ultimately, the sum over a bunch of terms like this. So one of these terms must be like, kind of big. We've picked the biggest one. So we're definitely making progress in the right direction. The question is really just, how much progress are we making? So when we weren't worried about calibration, the answer was always we were making alpha progress. Now, the problem here is that, like, alpha is bounding the L2 calibration error, which is the sum over a bunch of terms that look like this, where there's one term for every element in the range of our function. Okay, so if the range of our function is m, okay, then, that's pretty good. Like, we know that there has to be at least one term that's at least alpha over m, right? Because, the thing that we know is larger than alpha is the sum over all values v of, like, this expression. So if we're summing over m of these, one of them has to be at least alpha over m. The problem is, and this hasn't come up previously, it didn't come up last time for group conditional guarantees because the range of the function never came in. We weren't conditioning on the values, and so there was no, like, progress was just alpha. It wasn't alpha over m. It did come up when we were thinking about the iterative algorithm for regular calibration. We said, okay, the progress at every round is alpha over m, but it wasn't a problem then because m was fixed. Because for regular calibration, this iterative algorithm could only decrease the range of the function, right? Like, either, right, you'd shift one bucket, the buckets sort of were all disjoint, and so either you'd keep the range of the function the same, or two of the buckets would, like, collide, and the range of the function would actually get smaller by one. So you knew then that if the model started with only a range of only m values, that would be a invariant throughout the run of the algorithm. But here it's not true, right? These shifts can actually increase the range of the function by one because the groups aren't disjoint. Okay, so, like, the problem is, even if f starts out with some range m, the rate at which we make progress might slow down as we go on, right? Like, because every round, the size of the range can increase by one, which means we're going to be making progress more and more slowly if we just, like, try to apply this lemma naively and don't change the algorithm at all. Okay, so it's going to be a simple fix, but, like, is the problem clear? Okay. And it's not that, like, you could analyze, like, the algorithm would still converge basically because, you'd sort of be making progress at round t at a rate of, 1 over m plus t, which is a convergent series for any m, but it would take a really long time. So, yeah.
This might be a silly question. So can we compute, like, the update for each fx and gx combination, like, all together in the one shot?
What do you mean?
Suppose that initially I have, like, partition of the range, like bucket, and I have, like, k groups. So I actually have times k with the partition of the input space.
I don't know what you mean by partition, because remember, the groups are not disjoint.
It's hypergroup. Yeah. I regard each of the fx value and each group as a one group. So we will actually have times k group.
Okay, but crucially, these groups are intersecting.
Yes, that won't be like a problem since
Okay.
we actually allow for intersection on the overlap. We actually allow for like overlapping group.
Oh, no, but the difference is, so you want to like you want to define these pairs V cross G as groups.
Yes.
But last class, the groups were sort of defined exogenously from the model, like whether you were in some group didn't change after we did an update. Here, if the groups are defined in part by the model, that's the main conceptual difference between like calibration and just sort of group conditional things. Like when you do these updates, you won't, like people will be in different groups now.
Yes. So I'm wondering what is the difference? Because I can actually compute like the update like this lambda G, or if the partition based on like the initial partition of the fx.
Okay, so you're saying, okay, so you're saying, I guess you're not proposing like what will ultimately just be like a one-shot algorithm, like what we saw last time. You're proposing an iterative algorithm where we take like do like linear regression every step or something.
No, I'm actually thinking about like the one shot.
Okay, then I don't see how it's going to work. So you could, in principle, right? You could say, okay, like fixing FT, I have now a bunch of intersecting groups that are defined by FT and also the group. Okay, I could, I guess, run like the one-shot algorithm from last time for getting group conditional mean consistency for those groups. But I don't see why that would imply multi-calibration, because after I did that, I would be sort of marginally mean consistent for the groups that are now defined as the intersections of G and the level sets of yesterday's model that I started with. But the groups that define multi-calibration for this model are the intersections of G and the level sets of today's model that you just computed. There's the self-referential aspect. So like you'd sort of be multi-calibrated with respect to like the level sets of yesterday's model, but multi-calibration actually requires sort of mean consistency with respect to the level sets of the model we're talking about. But it is possible that rather than doing one of these updates at every step, you could run like the linear regression based algorithm last time that sort of gets one-shot multi-group consistency at every step, and then repeat it. And it would be interesting if you could prove that that algorithm had better bounds of some sort. I don't know if it does, but that, I haven't thought about it. So that would be an interesting thing to think about.
Just to be clear though, we're still in the batch setting. So there's
This is the batch setting.
Like a one-shot algorithm works for everything you're doing, which is find the Bayes optimal classifier. Because we still assume we have that information, right? So
well, so ultimately we're interested in, so it's true that like F star, which just outputs the expected value of Y conditional on X, is multi-calibrated. But we're going to be interested in sort of doing this within sort of a finite sample kind of way. And we don't have the information for F star.
if I did a one-shot thing, which is I looked at every single point, right? Or every single like unique point. And I looked at like what its average is, right?
Well, you in general from a sample, you only have, like there's no, I don't know what you mean by its average. Like I have one point that looks like Natalie, and I can see, your label, like, did you come to class today? Yeah. And there's no average, right? Like it's one, but like I don't know if I sampled a bunch of Natalie's, what the average of the Y would be, because I only have one.
Okay, so maybe this isn't obvious then, but it seems to me like if you have like the best thing you can do for sure, right? Even in the sample, is to like simulate the Bayes optimal by taking all the information you possibly can and saying like for every single particular point, like I'm gonna estimate what the mean is for this particular like unique set of parameters, and like this should get me as close to any notion of calibration. So
I think what you're saying is, like come up with like a lookup table, basically. Like like if I only have one sample of each type, as I would expect to in a large feature space, if I've only taken a small number of samples, like the mean, like the conditional label expectation in the sample would just be 0 or 1. It would, for every point, it would be like the actual realized label. And so it would, you know, it would be like multi-calibrated like on the sample, but it would be very, very badly calibrated on the distribution. You would have just overfit to the sample. So like, although it's true that at the moment, we're sort of imagining that we're operating directly on the distribution, the operations that we're doing here only involve taking expectations over large sets, which is going to be what's going to allow us to prove like good sample complexity bounds.
Sure, but if you did that algorithm and then we only evaluated over large sets, right? Then that problem would go away.
I don't, well, maybe the question is like how large, right? Like, so, you know, the goal here is going to be to get sample complexity bounds that scale with things like, you know, the question is ultimately when we, in the second half of the class, prove like sample complexity bounds for an algorithm like this, what's the main question going to be? It's like, if I want to be alpha multi-calibrated out of sample, but I'm going to run this to be, you know, to be like alpha prime multi-calibrated in sample, how big does n, the number of samples, have to be to get alpha prime and alpha to be close to one another? And like good answers are going to be things like, you know, polynomial in, you know, 1 over alpha, and hopefully like independent of like, you know, other sort of complexity measures. But like, so suppose the distribution was, you know, what is x? We haven't been talking about what x looks like, but to make things concrete, suppose every example is described by d binary features. So there's 2 to the d possible x's. Okay, so I think like to try to learn the Bayes optimal classifier, I would need to have seen every one of those possible x features many, many times, so I could average over the resulting y's. So like the sample complexity there would be exponential in the dimension of the data. It would be like 2 to the d. And d could be as large as we want. So our goal is going to be to have sample complexity bounds that actually like are independent of the complexity of the distribution and depend in, you know, mild ways just on like alpha and maybe g.
Okay, that's interesting. Yeah, because I guess I was thinking about all of this stuff that we were doing. It's like, oh, like this is all like inferior to this, like, you know, like looking at all the different data points individually, but it'll be more relevant when we start doing it online. But I see what you mean. Like at this point, the problem getting complicated enough that actually like this makes sense to just do for itself.
Or yeah, I mean, like you imagine the same question in like a, you know, more standard machine learning class. You could say like, what are we doing all of this like deep learning and decision tree and regression stuff? Like, why don't you just take the Bayes optimal classifier? Like, it's true that would minimize whatever error metric you want typically, but the problem is we don't have, that's not something that you would have the information to do unless you had somehow gotten many samples of every possible x in the support of the distribution.
Yeah, I guess I feel like maybe Bayes optimal is not quite the right word, but like, you know, the same problem applies here, that, you know, you are applying this process relative to a particular sample, which is not the entire distribution space, and so it's going to be limited in the same way, right? You're gonna compute your mean. I know we were talking about like samples last time, but like, is this, I guess maybe my question is, now we move to the setting, right? So you're saying like, okay, you know, you suspect that at this point we're looking at like maybe there's some like for a lot of previous stuff we've done, we sort of said like, okay, you can do this, but you could also do this other thing, right? Like in some ways this is a little silly, right? So at this point, are you claiming that this is the thing that you would do?
Okay, so maybe 2 things. So previously we have seen iterative algorithms that look like that, and then I said, okay, but it's a little silly to use them. There's this other thing. But the other thing wasn't like compute the Bayes optimal classifier. It was run a simpler one-shot algorithm.
Yes.
And in particular, we had the ability to prove good sample complexity bounds for those algorithms. Now, in general, what is the property of an algorithm that's going to allow us to prove good sample complexity bounds? We should interact with the distribution only in ways that are possible to simulate with small numbers of samples. In particular, like, how does this interact with the distribution? Ultimately, it only requires looking at expectations over reasonably large sets, right? Like we just have to like average over the labels for people that fall into some like reasonably large set that are in some group and have some value V. And like, that's the kind of thing we can do from small numbers of samples. That's like, you know, a law of large numbers kind of phenomenon. If your algorithm interacts with the data in some other way, then you have to start thinking about how you would, you know, like do it from samples and you know, it might be hard.
Right, that's fair. Like in particular, even last time before we were looking at, when we were just looking at mean multi-calibration, I think that like my like intended approach would have looked something like looking at all the different possibly exponential number of like intersections of all the subsets and finding, and like we know we can do better than that. We don't have to worry about all of these.
That's right. And in particular, like last time for mean, for group conditional mean consistency, we gave algorithms that did have good sample complexity bounds and didn't depend at all on, for example, you know, like the dimensionality of the distribution, right? The distribution could have been continuous. Like we had no dependence on the complexity of the distribution at all. That's the kind of thing we want.
Great. Okay, thanks. That's super helpful.
Okay. Good question. Okay, so just to remind us, we have this progress lemma, but like the problem is because the sets that we are making progress on are defined by level sets of the model. And every time we take a step, we increase the range of the model. We're potentially making sort of ever finer and finer like fine tunings of this model. And so our progress might be really slow. Like even though this thing is a convergent series for large M, it's a very slow one. Okay. So, you know, we have to fix that. And we're going to fix it in sort of a very, oh, yeah.
I'm sorry, can you explain again why it's a problem?
Yeah. So let's think about how like the analysis would go in maybe a comparison to the analysis we had last time for just these group conditional mean consistency guarantees. Right. So last time our progress lemma said something like this. Okay, like we performed updates on buckets defined by groups, but not defined by level sets of the model. And the definition of not satisfying group conditional mean consistency was that there was a group such that this product was at least alpha. And so we made alpha progress every time. Now, the definition of group conditional, the definition of multi-calibration is that there is a group such that the sum over all of the level sets of the model V of this quantity is at least alpha, which means that if the range of the model has size M, then we know that there's a term here, a level set and a group that is at least alpha over M. So today we will make progress alpha over M. But in doing so, we have increased potentially the range of the model by 1. So tomorrow we won't make progress alpha over M. We'll only make progress alpha over M plus 1. And the next day we'll only make progress alpha over M plus 2. So like the problem is, as we perform these updates, we are sort of slowing down the algorithm. Does that make sense?
Yeah.
Okay. Other questions? Okay, so we're gonna like fix it in the natural way. We just need to, you know, be a little careful about it. So like the problem is like, you know, at the moment as we've written things, we're doing these updates sort of like to decimal precision. Like we're saying, okay, you know, what is the exactly what is the expected value of the label conditional on the prediction and group membership. And if this is an interesting distribution, probably every time I estimate a number like this while running the algorithm, I get a slightly different number, right? Like, you know, and so I really will be growing the range of the algorithm. But, you know, if this number differs, you know, if these numbers are, or since ultimately I'm just aiming for approximate multi-calibration where I have some, you know, error tolerance alpha, I don't need to estimate these quantities to decimal precision. I could pick some fixed level of precision corresponding to some discrete range, and I could estimate these quantities like up to the precision of that range, meaning estimate them and then round to the closest thing in that range. Okay, and that would, like, just adding a rounding step here would guarantee that the range of my mechanism can never, you know, exceed the, like, you know, 1 over the precision to which I'm rounding. Okay, so like that's what we're going to do. And so we just need to like define the rounding step, and then we need to, it's going to like mess with our progress lemma a little bit, because our progress lemma at the moment is premised on making these updates to decimal precision. And so we're going to need to like argue that the rounding step doesn't mess too much with our progress lemma. And to do that, we're going to have to figure out like, okay, what is actually the precision to which we can round to? Okay, so that's the plan. All right. So let's use this notation. Let's let 1 over m in brackets denote the following collection of m plus 1 grid points. Just multiples of 1 over m, 0, 1 over m, 2 over m, up through m minus 1 over m and 1. Okay, so there's m plus 1 discrete grid points here. I've just like chopped up the unit interval at multiples of 1 over m. Let's define a rounding operation. Let's say that, I've got some, you know, like real value in the unit interval. Think about maybe like a quantity that I've just estimated. Let's round, if I say I want to round this value v up to precision m, what this operation spits out is just uv prime in this discrete grid that is closest to v. Okay, so just snap it to the closest thing in the grid. And I want to note that if v is what I get by rounding v prime, or v prime is what I get from rounding v, then v and v prime are within 1 over 2m of one another, right? Because I've got this grid, the distance between the grid points is 1 over m. And so, you know, any particular point that I'm rounding, either to the closest grid point, either to the left or the right, will only have to move half that distance. So the distance, yeah, the error I introduced by rounding is 1 over 2m if I'm rounding at the discretization of m. Okay. So let's fix up our algorithm so that it'll work better. V2. Okay, so first of all, we're going to start rounding things, and we need to know what precision to round them to. We're going to use precision exactly 1 over alpha. Okay, so m is 1 over alpha here. And let's say that, you know, who knows what model we've been given initially, what its range was. If its range was not already bounded by M, let's round the whole model, by which I mean rounding every entry of the model. Okay, so let's say that F0 is what I get from rounding at granularity M. Okay, so just round every output of the model. And now the only difference is let's say that V hat is the quantity we were previously updating with respect to. So this was like the conditional label expectation that we estimated to like decimal precision. We're not going to use that anymore. We're going to say the quantity we're going to use, which I'll still call V prime of t, this is just what we're going to get by rounding V hat. To this granularity M. Okay, and then the rest of the algorithm is the same. Okay, so let me make sure everyone understands the small changes I just made. Okay, so edit distance was pretty small. The point is now we've decided to work, instead of in decimal precision, we've decided to work on a grid that has granularity exactly 1 over alpha. Okay, and whenever we have an update, we round the initial model. So our initial model, already has range just in this discrete grid of size 1 over alpha plus 1. And whenever we do an update, we make sure that we don't update to decimal precision, we update to some point also on this grid. Okay, so now the range of this algorithm is always restricted to this discrete grid. And in particular, it's bounded by 1 over alpha. The size of the range is 1 over alpha plus 1. And what that's going to help us do is argue that we're making sort of reasonable amount of progress at every round. We no longer have this problem that an update will forever increase the size of the range by 1. Yeah.
So do we know whether or not this was a necessary change? So I understand why it was hard to reason about it before, but we now have added in, but is do you know that there's no way to actually that this algorithm actually has a slow convergence, in some hard cases?
Let's see. So first of all, even with the analysis we have, it would eventually converge, because again, this is a convergent series. We're making slower and slower progress, but we'll get over whatever finish line we set for ourselves. I do suspect that this algorithm as written probably does converge that slowly, because
Or as in the one that was written before V1?
Yeah. Like before we did the rounding, because it really is only updating one level set at a time. And it's only updating one level set at a time, and sort of the average size of the level sets is getting smaller. However, now that I am hearing the various comments that have been made in class, I do suspect that one way to get around this, if you didn't want to round, would be to say, okay, taking our earlier suggestion, I'm not going to update one level set at a time. I'm going to update all of the level sets simultaneously using this linear regression algorithm for group conditional mean consistency that we developed last time on, yes, the groups that are the intersections of our groups G and the level sets of model FT. Update all of those simultaneously with linear regression. Now, we're not going to be done. It's not a one-shot algorithm for multi-calibration, because again, the groups on which we need to be mean consistent are defined by self-referentially by the model. But it would solve this problem that I think no matter how many level sets there are, we would make alpha progress, not alpha over the number of level sets progress. So in fact, probably if you do that, you don't need to do the rounding. And in fact, it would converge, I guess, in a, like what we're going to get here, right, is that the progress, since the number of level sets is 1 over alpha, looking ahead, what we're going to get here basically is that we're going to converge in 1 over alpha squared many iterations. This algorithm would make alpha progress every round, so it would converge in 1 over alpha many iterations. So the sample complexity might be annoying, but at least in terms of like iteration complexity, that probably not only avoids the rounding, but speeds things up.
So we need to know how fast 1 over n plus 1 over n plus 2 converges, right?
Well, we don't need to because we're rounding, but
No, we're out.
you mean like if I didn't add the rounding step, you'd have to like analyze this thing? Yeah.
And suppose we round to n steps, like this sum is 1 over n plus 1 over n plus 1 to 1 over n. This is something like log n minus log n, right? Which is log n over n. So I guess in 2m over alpha steps, this algorithm will be stopped. I'm not sure why this is so.
Okay, so tell me again. So you're saying
So we
so basically, right, like the squared error is gonna potentially start at 1 and drop to 0. So we need, the question is, right, so we're gonna have like, something that's like 1 over m plus 1 over m plus 1 plus 1 over m plus 2 plus whatever 1 over m plus the total number of iterations. And we need, the question is, what is t such that this is bigger than 1? And what is the answer?
So I guess 1 plus 1 plus 1 over 2 plus 1 over 2 to 1 over n is something like log n, right? So this thing is just log n plus t minus log n minus 1, right?
Okay, so you're saying if I, okay, squinting a little bit, the sum from 1 to 1 over m plus t, right, that's like log of m plus t. So this is like, right, okay, so this is like, okay, so this is kind of like log of m plus t minus log of m. So it's like log of m plus t over m. Okay, I see. And right, so we want this to be like bigger than 1. And so okay, so you're saying if t was m, it would be like 2m over m, which would be like log of 2, which would be like 1. Yeah, okay, maybe that would be fine. So then the total number of iterations would be, sorry, you're saying it would be m. For whatever m you happen to choose. Okay, interesting. So just to foreshadow what we're going to get that the total number of iterations is, like 1 over alpha squared. But of course, the m we're using is 1 over alpha. So yeah, when would you want either thing? So basically, like, I guess you could do that, and you'd get some convergence bound as a function of whatever the range of the function was. What we're going to do with the rounding will artificially constrain the range of the function to sort of the smallest thing we can, still consistent with alpha multi-calibration, and we'll get a convergence bound that depends on alpha. But you're right. I guess the convergence wouldn't be so terrible for that one. Good point. Good questions. Okay, so we haven't even analyzed this yet, and already 2 ideas for a new algorithm. One, just don't do the rounding, still works. The other, at every step, run the linear regression mean conditional or group conditional mean consistency algorithm from last class, maybe reduces the number of iterations to 1 over alpha. But maybe like actually just doing this without the rounding already gets 1 over alpha if you said M was 1 over alpha. Right, so maybe you could just analyze the algorithm just by rounding the initial model and then not rounding anything subsequently.
And then if you do that, you'll do much better, right? Because we're saying that you would get a 1 over alpha as opposed to 1 over alpha squared convergence.
Does seem like you'd do better. Yeah, wait, but how can that be? I feel like the rounding shouldn't make you do worse. Okay, so why don't we proceed analyzing the algorithm with the rounding, but homework problem. We're going to get some sample complexity bound at the end of this that you'll see actually depends in an integral way on the convergence time of this. Like the convergence time is not just like a computational consideration, it's what's going to control our sample complexity. So it would be interesting, so if you had a version of this that somehow was more clever and converged more quickly, that would actually lead to like concrete improved bounds in terms of sample complexity. So I'm going to go through the analysis, assuming we're doing the rounding, but homework question, keeping in mind that maybe we don't need to do the rounding, figure out if you can get a better sample complexity analysis by not doing it. I think that would be a new result. Is the question clear? We haven't done the analysis of this yet, but I guess, yeah, it's not totally clear that you can't just directly apply this progress lemma. Yeah.
I don't have questions about the convergence. I guess it's more towards sample complexity. Because like, as we sort of said, that right now the algorithm is defined where V2 or V prime VT hat has access to the actual distribution. In practice, we don't have that.
That's right.
So we're always estimating it. So like, I'm not really concerned about convergence so much as whether that it like.
Yeah, we're gonna after the
unbiased estimator for that.
After the break, we're gonna need to prove a theorem about that.
Do you have any like?
By the way, we're not so like those words you said are nice, but like being consistent and unbiased aren't really relevant here. What we're most interested in is that like whatever our sample estimate for this quantity is just close numerically to the real estimate. Because what we're gonna end up saying is the convergence analysis is gonna say that we're sort of multi-calibrated in sample. And then after the break, we're gonna need to prove a theorem that says, if we run this algorithm so that we're alpha multi-calibrated in sample and we ran it on a sample of n points drawn IID from some distribution, then we're like, alpha plus blah multi-calibrated out of sample, where blah is going to be some error term that goes to 0 with n. So like, it's not really, like what we need is that our estimates get better and better as n grows large, but like if they're a little biased or something, that's okay.
Okay, so like a soft consistency.
Yeah, like we do want that we get the right limiting behavior.
So I guess one of the things I struggle with is the balance between updating something with a sample estimate of the expectation to sort of override the original F value that we had that was trained on more data. So it's not like we're looking at a very specific group that has like the same value from the original model for our most recent update and regroup.
Mhm.
But yeah, we're like just very specifically looking at like a very small percentage of the data, whereas the original model was using sort of like neighboring information too.
That's right.
Yet
Now,
doesn't fit.
now remember, like you might, like the concern you're raising also might be applied in sample, right? That somehow by fixing things for the group, we're making somehow the model worse in aggregate. But of course, our potential analysis is based on this global squared error. So these updates are error improving. So you're right that like, it is not a priori obvious that like we're not just overfitting, like we do have to prove a bound, we have to prove a theorem relating in and out of sample quantities. But like we will be able to do that. And the reason we will be able to do that is sort of, okay, maybe foreshadowing a little, two things. For any particular model, maybe you can believe that I can estimate on a data set its multi-calibration error. Like that's for like a single model, I can estimate on a data set its multi-calibration error because it depends basically just on averages of quantities that look like this. And for groups, for quantities for which we're conditioning on some tiny event, they sort of don't matter because in our L2 multi-calibration error expression, they get very little weight, right? Because it's an expectation over the level, the value of the level set V. So the way the out of sample bound is going to work is we're going to say, well, if this algorithm converges quickly, then there's actually not that many distinct final models it can output. Because at every round, this update depends on the choice of a group, there's finitely many of those, and the choice of a level set. There's only 1 over alpha of those. Right. And so, there's only a reasonably small number of one-step updates we can make. And so if we converge in a number of rounds T that is reasonably small, there's only a reasonably small number of models we can output at all from the small sequence of these updates. And since for any particular model in and out of sample, we can estimate multi-calibration error, we can sort of like union bound over all of them. That's how the analysis is going to work. Does that make sense? Okay, we'll see if it makes more sense when we do it. Okay. But because of this sketch, right, like because we're sort of counting models as a function of the convergence time of this thing, that's going to be why if you have a theory for a more clever convergence analysis that gets faster convergence, it's going to directly lead to better sample complexity bounds. Okay, so we need like a version of this progress lemma that takes into account the rounding. So the claim is that with the rounding, if I look at the change in squared error at round T, this is at least size of the bucket we're updating on times the same quantity that characterized our last progress lemma, where now, V hat is the same thing that we used to call V prime. This is the estimate to decimal precision. But now, the rounding is gonna sort of pull us backwards a little bit by an amount equal to 1/4m squared. Okay, so the progress is gonna be a little bit slower because of the rounding, because we sort of make the progress we would have made before, but then we, make a little progress in the wrong direction. Okay. So let's consider like the hypothetical model that we would have ended up with by doing this one-step update had we not done the rounding. Okay, like the model we would have updated to in V1 of this algorithm. Okay, so let's call that ft plus 1 hat. It's just the model that we would have updated to starting at the same place, starting from ft, if we had updated to vt hat. Okay, so it's just the update we would have done with the decimal precision estimate, like had we not done the rounding. Okay. So, like we already know the progress that we would have made had we done that update. That was what we analyzed over here. So we can now sort of decompose our progress into two parts. All right, so we're interested in, the change in squared error between model ft and model t plus 1. We can write that as the difference between the change in squared error between model ft and model f hat t plus 1, this hypothetical model. The difference between that and the change in squared error between the hypothetical, between tomorrow's model and the hypothetical model. Okay, like all I've done is added and removed the squared error of the hypothetical model, right? Like this is just the squared error of today's model minus the squared error of tomorrow's model, the thing that I want, minus the squared error of the hypothetical model plus the squared error of the hypothetical model. So I haven't changed the expression. But now we've got two terms that are a little easier to understand. Like in particular, the first term is what we already bounded in this lemma here. Okay, so this is equal to the size of the level set on which we're updating times vt minus vt hat squared minus the change in squared error if we were to take our updated model and sort of update it again to the value before the rounding. Right, and we can think of this really as an update as well, right? Because the value before the rounding is really the thing that we would have, right? Like that's the value, v hat of t. This is the true conditional expectation of the label on that level set. Okay, like this model ft plus 1 is, some kind of poor substitute for that. It doesn't have the true conditional label expectation. It's got this rounded value. Okay, so this second update is exactly of the sort that we know how to analyze, right? We're updating on the same level set, and we're updating from an incorrect value on that level set to a correct value. Okay, so like, you know, basically this lemma applies once again there.
Sorry,
Yeah.
the second, like, isn't that larger or equal? The second one.
It should be exactly equal because this is exactly equal. I'm just applying this lemma.
No, but here,
So this should be literally just an application of that lemma. The thing that's called ft plus 1 there is now called f hat t plus 1. Okay. Now remember, like, you know, like we know what this is going to look like, right? Like this term is also an update of the form that this lemma analyzes. It's just, you know, the thing that we don't quite know is how big is the update? What is the difference between v hat t, the numerically precise value, the sort of value that this model ft plus 1 hat takes, and vt prime, the rounded model that this other function ft plus 1 takes. But we do know a bound on that because we're rounding to the nearest grid point, right? Like in particular, we know that vt hat and vt prime are less than 1/2m apart, right? So we know that this is at least well, the progress we made on this update or let's say for now exactly equal to the progress we made on this update minus progress we made on this update.
This update, you mean when you did the patch before the round and then patch after the round?
Yeah, so consider, right, the algorithm's actually doing the patch from ft to ft plus 1.
Yeah.
In this argument, I'm asking you to consider this hypothetical model that we would have gotten had we started with ft, but in fact did the update with the numerically precise quantity vt hat. And then we noticed that the change in squared error can be written as the difference between the decrease in squared error if we start with ft and do the numerically precise update, and the minus the decrease in squared error that we would have gotten had we started with the model updated with the rounded value and updated it to the model with the numerically precise value. Okay. And so we're just saying, okay, well, we know exactly what each of those differences are, right? They're defined by the measure of the set we're updating on, which is the same in both cases, times the squared change, times the sort of squared shift that we've made there. Okay. And we know that the shift between the rounded model and the numerically precise model is less than 1/2m. Right? So we know that this is at least the measure of the set we're updating on times VT minus VT hat squared minus, okay, 1/2m squared, that's 1/4m squared. Okay. Which is the updated progress lemma. So same as before, except now, you know, we make progress, then we like backslide a little bit. Okay. So what's the final theorem? Given any model F, any collection of groups G, any distribution D, this algorithm, multi-calibrate, halts after at most 4/α² many rounds. And outputs an alpha multi-calibrated model. And moreover, if you're interested in the squared error of this multi-calibrated model, it is at most the squared error of model F0, which admittedly we applied a rounding operation to, minus the number of rounds we ran for times α²/4. Okay, so if you were, so once again, right, this is sort of going to fall out of the analysis because squared error is our potential function. Every round, right, the way the analysis works is going to decrease the squared error by α²/4. And so in particular, if you run for t rounds, you've decreased the squared error of the thing we started with by, t times that amount. Now, the catch here, of course, is that you might have slightly increased the squared error of f at the initial step when you rounded it to these discrete bins, which perhaps is which of course you can bound, but perhaps is an advantage of the proposal that we not do the rounding at all. If we didn't do the rounding at all, every step would strictly decrease squared error for the original model as well. So if you don't want to lose even terms related to alpha in squared error, I guess you could do this without the rounding.
Wait, you're saying we round F0? I thought we weren't rounding F0, we're just rounding as we go.
Well, what we want is that the range, but like it could be that like F originally has some continuous range and then we're screwed.
Okay.
So we do start, like everything is sort of on the discrete grid here. So if you wanted a strict decrease in squared error from F, and F had a range already M that you weren't shy about running in time proportional to, then I guess you could do it without rounding and the decrease in squared error would decrease directly from F. Okay. So let's prove this. It's quite fast, and then I'll give you guys a break before we move to out of sample bounds. Okay. So, if we find ourselves at round T of the algorithm, and we're not done yet, right? So in particular, if ft is not alpha approximately multi-calibrated, okay, like what does that mean? Then there must be some group G such that the squared calibration error of our current model, conditional on being in group G, is at least alpha over the probability of being in group G. That's just the definition of, multi-calibration means for every group, the conditional calibration error is less than alpha over mu of G. So if you're not multi-calibrated, there must be some group for which it's larger. And so in particular, like expanding that out, what does that mean? It means that on that group, if I sum over all of the elements of the level set, all of the elements of the range of ft, of the probability that the example is in group G and that it is labeled with V, of the difference between V and the conditional label expectation given V and membership in group G that this is at least alpha. Okay, this is just sort of expanding out the definition of calibration on the conditional distribution and multiplying both sides by the measure of G. And so this is a sum over all of the elements in the range of F. And so like all of those terms are non-negative. So in particular, since the range is of size m plus 1, in particular, there must exist some V such that this term is at least alpha over m plus 1. Right, because we're summing up m plus 1 terms. They're all non-negative. They sum up to alpha. In particular, what the algorithm is doing is finding the pair V and G that maximize this expression. And so in particular, since we know there must be a pair such that this expression takes value at least alpha over m plus 1, like the algorithm finds one that does at least as well. And so we just apply our progress lemma, which is right here. Right, what was it? The decrease in squared error is at least the measure of the group we're updating on times VT minus VT hat squared minus 1 over 4m squared, which is at least, this first term, the measure of the group we're updating on, times the squared shift of the update. We just said that term was at least alpha over m plus 1. Okay. But we might slide back 1 over 4m squared. But remember, m is 1 over alpha, right? So this is just, substituting 1 over alpha for m everywhere. This is equivalently alpha squared over alpha plus 1 minus alpha squared over 4, which is at least alpha squared over 2 minus alpha squared over 4, which is alpha squared over 4. So the squared error decreases at every round by alpha squared over 4. Of course, the squared error starts at 1, or can never be more than 1, and can never go below 0. That means this can't happen more than 4 over alpha squared many times. Otherwise, we'd have negative squared error, which would be a contradiction. And well, each of the steps decreases squared error by alpha squared over 4. So if we run it for t rounds, squared error decreases by t times that much. Okay, so convergence of the algorithm in sample to multi-calibration with these shifts and simple rounding, with some very interesting questions about whether rounding is really necessary and whether you might get a better analysis by not doing it. So why don't we take 10-minute break and come back at, let's say, 12-minute break, come back at 3:45. All right. So a couple of things. I guess having thought a little bit more about the suggestion of not rounding, I guess unsurprisingly, it doesn't improve the convergence time. It just doesn't make it too much worse. We sort of noticed that if we didn't round, the convergence time would be something like 2 times m. Here, the convergence time is something like, the convergence time would be something, I guess, like m over alpha. Here, the convergence, or 2m over alpha. Here, the convergence time is 1m over alpha. It's just that m is also 1 over alpha, right? So it's not that it's like m over alpha squared. The alpha squared comes from the fact that m is 1 over alpha. But it does seem like the rounding is really only saving you something like a factor of 2 in the number of steps. So if you don't like the rounding, and maybe there are reasons to not like the rounding, like you want to improve on the accuracy of your like initial model, say, then you could sort of skip the rounding and not pay too much worse. Also, you can do all of this for quantiles too. It's in the notes. I won't go through it, but it's you now sort of probably can understand how it goes. The algorithm is going to look very similar. We're going to look for violations of conditional quantile consistency now, conditional both on group membership and the prediction of the model, and we're going to fix those problems. And the analysis will go through decrease in pinball loss rather than decrease in squared error. We were sort of used to this kind of thing now. And will require, as usual in these kinds of analyses, the assumption that the distribution is rho Lipschitz and the rho will come into the bounds. But otherwise, the analysis is exactly the same as we've done here.
Are there any like quantile-based extensions that look at multiple quantiles simultaneously?
you could, yeah, so I guess, right, like, and this is maybe sort of related to, as you're starting to think about the project. So maybe like stepping back for a moment, right? Like what have I been doing in this class so far? I've been sort of taking additional desiderata you might want your predictor to satisfy, and I'm saying, okay, like, why don't we ask for this one, or maybe both of them simultaneously? And I've been sort of going through and noticing that like very similar potential kinds of arguments work to analyze all of those things. So you could imagine asking for more things along these lines. So just to name a couple of things, suppose I have two predictors that are predicting different things. You could ask for something called cross-calibration, which means I want, so say, there are these people X and they have different quantities associated with them. There's not just one Y. They've got a height and they've also got a weight and they've got, some probability of developing diabetes and all sorts of things. And I might separately have a predictor for each of these things. I could ask that each of these predictors be multi-calibrated, for example. I could also ask that they be cross-calibrated, which just means my predictor for weight should be correct, not just conditioning on my prediction for weight, but conditioning on this other predictor's prediction for height, right? So you can ask for cross-calibration. And you can imagine, we're not going to go through that in this class, but you can imagine how it would work, right? You'd like simultaneously be updating these different models, and you'd be looking at level sets defined not just by the same model, but by the other models you're updating at the same time. And you'd perform patches not unlike these patches, and they would decrease squared error when you did it. Right, yeah, good. So like you should be thinking about not just the particular things we're deriving here, but all sorts of other things that would fall out of the same kind of analysis. So you very much can condition on more than one thing at the same time, and it would be interesting to find applications where that was like useful. Like basically, since many of these derivations are like kind of similar, what I'm hoping that you're getting is that this is like what we're seeing are a couple of instantiations of what is a much more general framework for updating things to be consistent with the data. And yeah, there's like a ton of different variations you could consider. Good question. Other good questions? Okay. So, we proved this theorem, but this theorem, it's like about running this algorithm like on the real distribution, which of course you can never do. What you'll generally do is you'll have a data set that consists of n samples that are maybe like drawn IID from this distribution, and you'll run something like this algorithm on your data set, or in other words, on the empirical distribution on the samples. And what you'd like to say is not just that you're multi-calibrated on the data set, but that you're multi-calibrated on the distribution. And in fact, like as Natalie pointed out, we didn't have to go to all this work to be multi-calibrated on the data set, right? Like we could have come up with the Bayes optimal predictor for the data set, otherwise known as just a lookup table, where I just predict that, for every example X, for which I've probably seen only one, the label is, the label expectation is just like the single realization of the label that I've seen. That's the Bayes optimal predictor for this data set, but it's not an interesting object. It has nothing to say about the samples I haven't seen yet. So the hope is that, since we've put more effort into deriving these algorithms than just like writing down the answers on our hand, which would have done it for, like if we really had direct access to the distribution, the hope is that we can run this algorithm on samples and it'll say something about the underlying distribution. So let's verify that. Okay, now I'm going to state for you a bound that when I proved it over the summer, I was like, all right, so this is going to be like a Chernoff bound. But it turns out to be like really annoying sequence of Chernoff bounds that takes up like 10 pages in the notes. So I'm going to like state the bound for you and tell you roughly how you would derive it. And it's basically you take the Chernoff bound and you whack every term with it and you propagate the error, but it's like super ugly. So I'm not going to subject you to it, but I'll tell you how you do it. And it's, you know, in the notes, and it's ugly, but here it is. The details are not, like, what I want to do basically is give you all of the interesting moving parts of the proof. And like, it's like a 12-page proof in here, and 10 of the pages are not interesting. So I'm going to skip those 10 pages. Okay, this is like the theorem that's the uninteresting part. It's like a technical lemma. Okay, so fix any model. Any group. And let's let be a data set sampled, consisting of n points sampled IID from the underlying distribution. Okay, so we've got our distribution and we've taken n IID samples from it. With probability 1 minus delta, if I look at the difference between the following in and out of sample quantity, that difference is small as a function of n, or goes to 0 as n grows large. Okay, so what is the quantity? Well, it's like the, this thing we've been analyzing, like the product of the size of the group and the product of the size of sort of a group intersect level set times the squared difference between the prediction at that level set and the conditional label expectation squared. Okay, so the claim is you evaluate that thing in and out of sample for any single model, and it's like kind of close. Okay, in more detail, if I look at that quantity and the underlying distribution, and then I look at that quantity on the data set. And the absolute difference between these quantities is bounded by something. Okay, and taking away all of the ugly constants, this is a quantity that is on the order of the square root of the measure set that we're interested in intersected with the group times log of 1 over delta over m. Okay, so let me tell you just like what this is saying, right? It's looking at this kind of quantity here that was sort of central to our analysis, right? For any group intersect level set, right? These kinds of things we condition on to talk about multi-calibration and to update our algorithm. Saying for any particular fixed model F, fixed group G, and I guess fixed prediction V. If we look at this quantity on the distribution and we look at this quantity on the sample, then it goes to 0 at the rate you would expect, 1 over root n, except it like goes to 0 more slowly if the slice of the data distribution that we're looking at, or rather actually, sorry, goes to 0 more quickly if the slice of the data distribution you're looking at is very small. Okay, so in the numerator here is the probability mass under the true distribution of the slice of the data you're looking at, right? The probability that points are in group G and are given value V. Okay, and you might think, okay, well, I have fewer samples of those points, so like maybe I would expect that it would hurt my estimation if those sets were small. But remember, the thing that we're claiming goes to 0 multiplies by that thing on the outside. So although this inner estimate does indeed get worse for small sets, that is made up for by the fact that we're multiplying on the outside. And so actually the estimation error is better for small sets. Make sense? And you can imagine how you would prove this, although, be lucky you don't have to, right? Like the Chernoff bound basically tells us that any quantity that can be expressed as an empirical average over a distribution converges to its expectation over the distribution at a rate of like 1 over root the number of samples you have. Okay, so this expression is made up of things like that, right? Like the measure of the slice of the distribution, that's just an empirical average, right? Like how many points fell into this slice. This conditional expectation, that's an empirical average. Although the annoying thing about this conditional expectation is the number of samples that go into it is not a constant. That's also a random variable. So you have to bound, right? So you have to bound that with a Chernoff bound. And then once you've done that, you can bound this with a Chernoff bound. And then once you've done that, you can bound this with a Chernoff bound. And then each of these has error terms that you have to propagate through. And well, this is squared. So the error terms, have cross terms. But anyways, you can do all of that and you get something like this. But there's nothing like deep going on. It's just like repeated hammering with a Chernoff bound.
So when we don't know anything about f of e, right? Can be anything.
Could be anything. That's right. But it's fixed.
So my question is, I guess, when you have n samples, how do you know how many of them fall into this f of t of x equal to v? We don't know anything.
So I guess like the only thing that
we know the density of these forms.
So I guess the point is the only relevant thing, I don't care about the structure of T if I'm asking how many points I expect to fall into one of these slices. I just care about the probability that they fall into one of these slices, right? So each point falls in or not as a Bernoulli random variable that has probability of falling in exactly this. And this term, yeah, so exactly. So this thing matters, and it shows up in the bound.
So in order to differentiate this result from like what you would get from like doing some sort of Bayes-Alpha approximation, right? Like the proof has to rely on like the actual.
To be clear, right, this is not the generalization theorem. This is a lemma we're going to use for the generalization theorem. So we have no result yet to compare to Bayes, because this is not for the model output by this thing. This is for a fixed model, fixed before we draw the data. Whereas the model output by this is a function of the data. So this is like a useful lemma, but not a generalization theorem yet.
Fix before you draw the data.
Right, fix a model, then draw the data with probability 1 minus delta over the data. Right, that's important for like a Chernoff bound. Like,
So this model doesn't get any access to anything in order to exist?
This has nothing about, so far we've said nothing about this algorithm. Because of course, this algorithm is going to produce a model as a function of the data set. So this doesn't apply yet.
So it's a
This is-
model that's independent of any.
This is
data.
just saying you have a model.
Yeah.
I don't know where you got it. It's your business.
It
But
can't be dependent on the data. though.
can't, well, it can't be dependent on the data. Yeah, because I'm
Well, it
gonna,
must be
like the data didn't
dependent.
even exist. Like you've handed me the model. And only then did I gather some data. And all I'm telling you is that whatever this quantity is that I can evaluate on the data, it's close to this quantity on the distribution. I'm not telling you that these things are small, for example. I'm just telling you that whatever they are, they're,
Oh, right. So it doesn't act as a distribution. The model. It could have another act, like it could have another sample, just not this sample.
could have.
Okay.
But, there's no assumption like that. This is just any model.
Yeah, I mean, it can't have anything except for D. The non.
Yeah, I mean, D did not exist at the moment you handed me the model because of the order of quantifiers. You handed me the model, then I sample D, and I'm telling you that I can measure, pick any G, pick any V, I can measure this thing on the data set, and it's like close to what I would get on the distribution and vice versa. Okay. But yes, like D is sampled after the model is fixed in this theorem. Okay, so we can prove this with lots of Chernoff bounds, but we won't. Scroll ahead. Okay, so, but you've put your finger exactly on like the gap between, like the thing we need to resolve before we can apply this theorem to like the thing output by our algorithm, which is that here the model's fixed before we draw the data. But like for the algorithm, it's exactly reversed. The data is drawn and fed to the algorithm. The algorithm computes all sorts of stuff from the data and then outputs a model. So we need something that's going to apply with like a, the order of quantifiers reversed. Okay. And what I want to say is that although the model output by this algorithm is not fixed before the data is drawn, it's a function of the data, it's actually not an arbitrary function of the data. There's a reasonably small set of models that actually are fixed before the algorithm sees the data, and the algorithm will choose amongst those, but it'll always output a model from this fixed set. And so what we're going to argue is that this is true, something like this is true, the parameters will get worse when we union bound, simultaneously for every model that this thing might output. Those models are fixed before the data is drawn. And so even though it's choosing amongst them as a function of the data, since this kind of thing will hold uniformly over all of the models that the algorithm might output, it'll in particular hold for the one output by the algorithm. That's going to be the form of the claim.
Sorry to slow you down, but I think I maybe still look like what's happening here. Are you saying which direction is this bound going?
This is smaller than, this difference is small.
For any model that first doesn't see the data? What if it's like really, really bad?
It's not saying that these quantities are good, right? Like each of them might be large. It's saying
Yeah.
they're close together. So it's just saying like, if I want to estimate, like suppose I really want to know this distributional quantity, I'm just going to measure it on the data and that'll be a pretty good estimate.
Okay, so like one of these objects is any model, right? On that. And then the other one is what? A model
Sorry.
after seeing some data.
So to be clear, these two quantities that we're taking the difference of are like, unless I've made a mistake, character for character identical, except wherever the distribution was written before, the data set is written, which just means
Okay.
instead of the empirical quantity, what fraction of the points are in group G and are
I see, you're right.
given model V, I'm estimating the expectation. Like the expectation over the data set, this is also an expectation over the data set, is just an empirical average. And the expectation over a distribution is like a true expectation. And it's just saying like the empirical average is close to the expectation,
Okay.
which it's analogous to saying, if I look at the average number of heads I get when I flip a coin sufficiently many times, it is close to the expected, fraction of heads I get if I flip it 1,000 times.
Just run through this app.
Yeah, but like it's saying some event is close, some expectation is close in sample and out of sample. The expectation happens to be defined by this F, but
Got it. Okay. Yeah.
otherwise, we don't know anything about this F. Make sense?
Yes.
Okay. So, okay, what I want to do is basically count the number of models this thing might output. Okay. So lemma is going to say fix any model F. Think of that as the input to this algorithm. Okay. Any collection of groups G and any alpha greater than 0, the approximation parameter we plug into this algorithm. There exists a collection of models, a set of models C such that for every distribution that we feed to this algorithm, in particular, any data set we feed to it, just corresponds to some empirical distribution. The model FT that results from running the algorithm is such that this model was in this collection of models that was fixed ahead of time, fixed just by the algorithm and its inputs, not by the data set we gave to it. And the size of this set, the models that, the collection of models that we know the algorithm is going to output even before we see what data set we give it, has size at most the number of groups over alpha squared raised to the power of 4 over alpha squared plus 1. Okay, so let me just sort of state the form of the theorem to make sure we're sort of grokking it. It's saying, look, we don't know exactly what model this thing's going to output. Like it is a function of the data. But we sort of want to apply a theorem like this that sort of requires we fix a model before we see the data, right? And the form of this algorithm is sort of the opposite. We, give it the data and then it gives us back a model. But we want to say, actually, before we see the data, because this is going to be true quantified for every distribution we might give it, before we see the data, we can already fix a finite collection of models that has size, merely exponentially large in alpha, in 1 over alpha, such that we know ahead of time, like that, whatever data set or distribution we plug into this thing, the thing it's going to output is part of this set that was fixed ahead of time. So in particular, again, jumping ahead a couple steps, we sort of want to apply like a theorem kind of like this uniformly to everything in this set C. And then we can say, okay, so in particular, it'll hold for the model output by the algorithm because it held for everything in the set C, and whatever data set we gave the algorithm, it was something in the set C. Does that make sense? Okay. And it's just a counting argument. Okay, so I want to note that suppose I wrote down a transcript of the choices made by this algorithm at every round. What are the choices? Well, every round the algorithm chooses a level set VT and a group GT, right? And it chooses to update to some new value VT prime. Okay, if you tell me those three things, VT, GT, and VT prime, that tells me what the model is tomorrow, right? Because the model tomorrow is a function of those three things and yesterday's model. Okay, so iterating this through T steps of the algorithm, if you give me, if I know like the model that was initially input to this thing, F, that's fixed up here. And then you give me the transcript of the algorithm. For every step it was run, you tell me what level set it updated on, what group it updated on, and what it shifted the prediction on that level set to be. You told me those three things at every round. That would be enough to define the model that it was output at the very end, right? Because each time if I have yesterday's model, then this triple tells me what today's model is. And then the next triple tells me what tomorrow's model is, so on and so forth. Okay. So the only thing we need to do is count the number of distinct transcripts that might be generated by a run of this algorithm, where a transcript is just a record of these triples chosen at every step, VT, GT, and V prime T. Okay. Right. So we just need to count transcripts. So, well, there are G choices for the group GT, right? There are 1 over alpha choices with the level set to update on VT. And there's 1 over alpha choices for the level set to update to VT prime. By the way, this is another reason to discretize. The generalization theorem might be tricky if you did things to decimal precision, because now we couldn't count transcripts in the same way. Now I'm remembering. Yeah. Okay. So that means that the number of transcripts length T is just, well, G times 1 over alpha times 1 over alpha. So G over alpha squared. That's the number of triples at each round, raised to the Tth power, because we for every iteration T, we can pick a new triple. Now, T, how long is the transcript T? Well, that's the convergence time of the algorithm, right? Like the T cannot be longer than we proved 4 over alpha squared. Okay, so T can't be larger than 4 over alpha squared. So the number of transcripts of length 4 over alpha squared, the number of transcripts of length T is, number of groups over alpha squared to the T. What we are interested in is the number of transcripts of length at most T, because it could be shorter than that. So we need to count how many transcripts are there of length 1 plus length 2 plus length 3 up to at most 4 over alpha squared. And that's just g over alpha squared to 4 over alpha squared plus 1. Okay. And that's it. Okay, so we've basically just counted the number of transcripts, the number of trajectories basically that this algorithm can take. And it's like not that many because it runs for t rounds. At every round, it just chooses a triple of objects from some finite domain. This is where the rounding was important. And we know that the transcript has, relatively small length. So there's just not that many functions. Does that make sense? Okay. So, we're almost there. Okay, the next small step is just to apply this, this theorem here, not just once, but simultaneously to every model in this class that the algorithm might output, to union bound over all of them. Okay, so this tells us something happens for a single model with probability 1 over delta. Okay, so if we want it to happen uniformly over all of the models in that class, we have to set delta to be delta over the number of models in that class. Okay, now the number of models in that class is exponentially large in 1 over alpha squared, but fortunately in this expression, 1 over delta shows up inside a log. So we're gonna inherit only a linear dependence on 1 over alpha squared, not an exponential dependence. Okay, so okay, so what's the lemma? Applying the union bound. Fix any model F, any collection of groups G, any alpha and delta greater than 0. Let D consist of n samples drawn IID from the distribution. And let F be the model, FT now be the model output by this algorithm. Multi-calibrate when I feed in F alpha G and the data set. Okay, so we're swapping the order of the quantifiers here. First, we're sampling the data, then we're running the algorithm to get a model out. Okay. With probability 1 minus delta for every group and every level set of this function. Let me just call this whole big difference here star, the difference between this quantity in sample and out of sample. Star is at most, okay, I'm just going to copy over this expression, except I will have replaced delta with delta over this. this is just applying this bound here uniformly over all of the, this many models that our algorithm might output. And like note that what we've done relative to this bound is sort of, ignoring the constants and low order terms and stuff. We've sort of made it worse by a factor of basically 4 over alpha squared. Why? Because 4 over alpha squared was in the exponent here. And that showed up inside the log. Okay, so by making the bound worse by a factor of 4 over alpha squared, it applies uniformly to every model that might be output by this thing. Okay, note, by the way, that like our generalization bound gets worse for smaller values of alpha. Why is that? It's because for smaller values of alpha, it takes longer for the algorithm to converge. And what we're doing in our generalization bound is counting transcripts generated by the model, which there's more of them if it takes longer to converge. Okay. So then finally, this isn't quite the final statement we want, right? Because what are we doing? We want to say if we're alpha multi-calibrated in sample, we're, alpha plus alpha prime multi-calibrated out of sample. So far, we've just proven that these two expressions are close to one another for the model output. And these things are like constituent terms in our definition of like multi-calibration error. Like basically we need to sum all of these up over the level sets of the predictor to get our multi-calibration error. And you basically just sum them up. So I'll state the theorem for you and again, not do the algebra to sum them up. I'll just note that there's like one little piece of cleverness you need to do when summing them up, because you're summing up over all of the level sets V, and the measure of the level set V shows up in the error term here. So you need to use the fact that, these things sum up to, the probability of the group. Okay, but you can do that. So what's the final theorem? Fix any model F, any collection of groups G, any alpha and delta greater than 0. Let D consist of n samples drawn IID from some distribution. Okay. Then with probability 1 minus delta, model output by our algorithm, multi-calibrate. When we run it, not on the distribution, but on the samples drawn from the distribution, is alpha prime approximately multi-calibrated on the distribution. For alpha prime, I'll spare you the constants that look kind of like this. For alpha prime, that kind of looks like the following. Well, there's two sources of error, right? Like basically, what we're going to be able to say is that, we have some level of alpha multi-calibration in sample, And we're potentially somewhat worse, and potentially the difference between our in-sample and out-of-sample multi-calibration is something. So there's a trade-off, right? Like we can make alpha smaller. That'll make our in-sample multi-calibration error smaller, but it will make our generalization bound worse. Okay, and so our multi-calibration bound out-of-sample is the sum of those two things. Right, so first of all, okay, we have alpha multi-calibration error in sample. That's unavoidable, that we ran the algorithm to get, we stopped when we had alpha multi-calibration error in sample. And then we have our generalization bound, which has terms that get worse with alpha, that sort of look like log of the cardinality of G over alpha squared delta over alpha cubed n plus the square root of log of the cardinality of G over alpha squared delta for alpha cubed n. So a bound that kind of looks like this, right? So like the exponent has already come out of the log and is responsible for some of the terms down here. Yeah. Okay, now we can, like alpha is a parameter we choose, right? Like we decide what alpha is, we plug that into the algorithm. So we should choose the alpha that minimizes this expression, right? So, choosing alpha optimally, just to minimize this expression, what we get is that alpha prime is something that goes to 0 at a rate of log of the cardinality of the groups over delta over n, all raised to the 1/5 power. Okay. So this is something that, first of all, goes to 0 as n grows large. It depends only polylogarithmically on the number of groups. So you can really ask to be multi-calibrated with an enormous number of groups, and what you pay for that in sample complexity and everything else is very small. It depends only logarithmically. Now we do have this like annoying, like when we're estimating, if we're estimating like a single out of sample quantity, we'd sort of expect the error to go to 0 at a rate of 1 over root n. And here, the error is going to 0 at like the substantial, like still polynomial, but substantially worse rate of 1 over n to the 1/5. And I don't know if that's optimal or not. So that's another homework question, like, can you get the 1/5 down to 1/4? The reason it's coming out of the analysis is that we have this 1 over alpha squared dependence on the running time of the algorithm, and our generalization bound depends linearly on the running time of the algorithm because it follows from counting transcripts. So our problem is, as we make alpha smaller, the algorithm runs for longer and our generalization bound gets worse, which requires that we pick alpha to trade off these two terms, which is where this, n to the 1/5 is coming from. But like, I don't know if that's tight, like extra credit if you get it down to n to the 1/4. Okay. Okay, so for next class, project proposal, and get this down to 1 over n to the 1/4. Okay. And I'll see you guys then.